So, how do we do this? So, we know that it is enough to compute reciprocal. Okay. So, what is the notation that I have? Okay. So, actually what we do is, what we need is, we need to compute this quantity, and actually what we need is, we need to compute 1 over y, okay, because once we get 1 over y, we can multiply that with x and get the result. So, how do we get 1 over y? So, what we will show is, we will not compute 1 over y exactly, but we will compute an under approximation of 1 over I. Okay. So, we will compute okay, let me write this. So, whatever agenda is going to be, let me write it. So, we will be computing a quantity, let us call it as y tilde inverse, okay, such that, what is the relation between y tilde inverse and y inverse? So, such that y tilde inverse minus y inverse is smaller than 2 to the power minus n. Okay. So, we will try to compute a quantity this, such that this is this. Now, why 2 to the power less than 2 to the power minus n? Because once we have this, so what are these x and y's? So, x and y's are n given, so this is not 2 n bits, so given 2 n bit integers. So, x and y are n bit integers. So, the maximum value that any of these can have, for example, the maximum value that x can take is 2 to the power n. So, x times okay. So, then let me write this. So, then x y tilde inverse minus x y inverse. So, this is what I want, and this is what I will be computing. What will be the difference between these two? So, multiplying this with x. So, how large is x? X is 2 to the power n. So, this is, how large is this quantity? Less than 1, yeah. So, this is less than 1, right, 2 to the power minus n into 2 to the power n, right. So, this quantity is less than 1, meaning is that it is some small. So, essentially what I will do is that, so let us say that I will call this as, let us say I will call this as t. So, essentially my answer will be, so this is actually a under approximation. So, y tilde will be an approximation of y. So, y tilde inverse will be an under approximation of y inverse. So, let us call this as t. So, the answer will be, either it will be the floor of t, or it will be t plus 1, okay, because the actual answer is at most difference 1. So, either it is this quantity or this quantity, and which quantity it is, we can easily check. We can just multiply both these quantities with y, and we can check that what is the difference between that and x. That should be less than 1. So, that is easy, but essentially we will compute this, or actually we will compute just this. T is this, the approximated product that we are computing. Okay. So, we will compute y tilde inverse, we will multiply that with x, we will set that as t, we will take the floor of that, and now the actual answer will be either this or this, that we can determine just by back calculating. Okay. So, now how do we compute y tilde? So, let u be equal to 1 minus 2 to the power minus j, where y is an integer that is less than 2 to the power j and greater than or equal to 2 to the power j minus 1. Okay. So, any number lies between two powers of 2 consecutive powers of 2. So, I just find that quantity for y. Okay. And again I can get this value of j using an NC1 circuit, because I just have to keep on dividing y by 2 repeatedly. So, basically I just have to check how many bits, I mean well, what is the position of the first one in the string y. Okay. Essentially that is what it is. So, I compute this value j, and let us say I set y is u is equal to this. So, this implies that one minus u is equal to y 2 to the power minus j, which implies that y inverse is equal to 1 minus u inverse into 2 to the power minus j. Okay. And one more thing, just a small technicality, but it is important, is what is the smallest value of j. Okay. So, observe that here j is at least 2. Why is j at least 2? Now, that actually depends on y. So, what is the smallest y that can be there? Okay. So, note that y is greater than or equal to 2, because if y is 1, then the answer is x. Okay. So, if y is greater than or equal to 2, that is the minimum value of y is 2, then well it is between, yeah, so it is between 2 and 4. So, 2 means that it is 2 minus 1, which is 2 to the power 1 is 2. Okay. So, j is at least 2. So, we will be using this fact later on. Okay. So, y inverse is equal to this. Now, we will see what is 1 over u inverse. So, this is nothing but 1 plus u plus u square. So, this is the infinite series 1 plus u square so on times 2 to the power minus j. Okay. And one more observation, what is the value of y into 2 to the power minus j? Okay. So, if I divide this entire expression by 2 to the power minus j, what I get is that y into 2 to the power minus j lies between, so this quantity, it lies between half and 1, right. So, essentially 1 minus u lies between half and 1. What does it say about u? So, if 1 minus u lies between half and 1, it means that u is greater than 0 and less than or equal to half, right. So, u is less than or equal to half. So, now we can come back to this. So, what is this? So, this is okay. So, now what we do is that we will set y tilde inverse to be the first n terms of this series. So, it is 1 plus u plus up to u to the power n minus 1 into 2 to the power minus j. So this is going to be our y. So now you can see where we are using powering. Okay, so essentially we are using powering to compute these powers of u. Okay, so this is y tilde inverse, and now we can verify this quantity, that y inverse minus y tilde inverse is equal to u to the power n plus u to the power n plus 1, so on, into 2 to the power minus j. Now each of these u's are less than half, so I can write this as, this is bounded by 2 to the power minus n plus 2 to the power minus n plus 1 plus so on 2 to the power minus j. J we know is at least 2. Okay, so even I take j to be equal to 2, this quantity is less than 2 to the power. So this sum, if you just look at this sums, if I take 2 to the power minus n as outside, this is actually equal to 1 plus half plus so on. So okay, let me write this as, okay, 2 to the power minus n, if I take as outside, this is 1 plus this sum is bounded by 2, j is at least equal to 2, so therefore this is less than 2 to the power minus n as we wanted. Okay. So 2 divided by 2 is, it is less. So anyway it is less than 1. Okay. So this is the analysis. So this is what we actually wanted. So what we want is to have y tilde inverse as this quantity. So now what is the algorithm? So now the algorithm is simple once we have the analysis. So first step is okay, compute j such that y lies between 2 to the power j minus 1 and 2 to the power j. Next step is compute u to the power, how do I get u? So u is equal to 1 minus y. Okay, so compute u, which is equal to 1 minus y into 2 to the power minus j. So we have y, we have j, so we can compute u. Third step is compute u to the power 0, u to the power 1 up to, we are going up to u to the power n minus 1. Next we compute y tilde inverse, which is equal to basically this summation 1 plus, we have seen this also, right? We have seen iterated addition also in NC1. So 1 plus u plus up to u to the power n minus 1 into to the power minus j. Okay. Then compute t, which is equal to x into this quantity. So determine which of this or is the answer. So that is the algorithm. So essentially, except for this third step over here, all the other steps are in NC1. So we have, so this is in NC1, this is just multiplication and well subtraction is just the same as addition. We have this is also just iterated addition, this is again multiplication and this is again multiplication. Okay. Huh? 2 to the power minus j multiplications. No. Shifting the decimal, yeah. So it is representation of decimal numbers, sorry, representation of fractional numbers in binary. Yeah. You are shifting the decimal, yeah. Okay. So this is the only step where we need oracle gates for powering, okay, because we don't know how to do powering yet, and the rest of it is in NC1. So this you can do in parallel, na? So all these, yeah, so here actually all the oracles are in parallel. So that's a good point. What happens, and yeah, so here actually it is just one level, okay. So given you have these n different gates which are computing all the powers of all the first n powers of u. So if the oracles are placed in series, even then it will be NC1. So there is a proof for that. The reason is the input size for all these gates, okay. So suppose, so let us say basically what you are saying is, suppose there is a path, okay, from an input gate to an output gate in an NC1 circuit. So this is, let us say, some NC1 circuit to an output gate, and here let us say I have several oracle gates along this path, right. Now the point is that the total length of this path is of course bounded by log n, because we can assume there are log n many oracle gates. So what is the okay, so what is the thing then? So sorry, what is your question? If so each G gate is NC1, okay. Yeah, apparently yes, the total depth will be log square n if you don't, but I think, I don't remember right now, but I think there is a proof which shows that if these log n gates are NC1 gates, then you can show that the entire circuit also is in NC1, and that kind of, I think the idea is based on the fact that the inputs are disjoint, the inputs to all those gates are kind of disjoint, okay. So basically if I have log n many input gates, and if each of them have depth log n, then well, the total input cannot be still more than n, so something like that. But anyway, so yeah, I cannot comment about it right now because I have to figure out what that proof is, okay, only then I can comment about it. But of course this problem does not arise for us, because this will only happen if these gates are in series, but here we are doing it in parallel. In fact, all the reductions that we will do, we will actually show they can be done in parallel. Okay. It can be n, yeah, it can be n. In fact, here it is taking u now. So, this gate G is taking u. So, a u is itself a n bit number, order n bit number, because it depends on y. Y is a n bit number. Huh? N square bits. Yeah, it outputs n square bits. Yeah, I'll try to come back to this question later on. This is a interesting question. I mean, so this is actually a general, I mean, a question about the general NC1 reducibility, but yeah. In fact, this result was actually due to Cook. This was a result in one of his papers, one of his earlier papers probably, where he showed that if you have function f NC1 reducing to G and G is NC1, then f also is NC1. So, basically the class of the NC1 is actually closed under NC1 reducibility. Okay. So, this was a result in one of his papers. So, we have shown this theorem. So, let us move to the next result. This is also, so yeah, so essentially what is the fundamental idea in this theorem? Okay, so the fundamental idea is that I want to compute 1 over y. Okay, instead what I am computing is a quantity like 1 over 1 minus some u, okay, and show that these two quantities are kind of similar, and then 1 over 1 minus u is nothing but it can be represented as a sum of a geometric progression. Okay, so it is a geometric series. Okay, so that is essentially the idea of this entire thing. Now let us look at the other direction, that is powering NC1 reduces to division. Essentially here what we will do is that we will do the entire thing in reverse in some sense. Okay. So, what we want to compute is, given x, we want to compute the powers of x. Okay. So, let x be an n bit integer and we want to compute all the powers of x. So, what I will do is I will define a number, a large number, let us call it as capital X, as, okay, let me show it pictorially first. So, I will have all the powers of x. I will start with I'll start with x to the power 0, I think. So, I will define x as being equal to, so I have x to the power 0, which is nothing but 1, then I will have x and so on. Finally, I have x to the power n minus 1. Okay. So, think of a large bit string, okay, which has all these powers of 2 and they are kind of separated. Okay. So, and we will assume that each of them are 2n square bits long. So, this I said at the beginning that any power of x up to x to the power n is at most n square bits, but I will add some extra zeros. Okay. So, basically x is this string which is concatenation of all these strings. So, now I can actually write x as something. Okay. I can write x in terms of these xi's. So, x is nothing but sum I equal to 0 up to n minus 1. So, there is a scaling factor 2 to the power n minus I equal to n minus 1, it is n minus 0 Doing it, oh, 2n square into n minus I, yeah. So 2 to the power 2 n square into n minus I times x to the power I. Okay. So this is my scaling factor which is getting shifted, and times x to the power I. Okay. Now what is this? So I can take the constant term outside. The constant term is 2 to the power 2n cube sigma, then I will have 2 to the power minus 2n square I into xi, so which is sigma I equal to 0 up to n minus 1 2 to the power minus 2n square into x whole to the power I. Okay. Now this is also a finite, yes. Thank you. Yeah. Okay. Now this quantity, okay, is okay. So how do I want to say this? So essentially, what can I say about this quantity? Okay, so this quantity, so this goes to, so what happens as n tends to infinity? Okay, so as n tends to infinity, this is a geometric series. So this will go to 1 over 1 minus 2 to the power minus 2n square into x as n tends to infinity, right. But what I have here is not as n tending to infinity, but just the first n terms of this series. So what I will do is that I will not care about that, I will just look at the value of this series as n tends to infinity, because beyond that the terms will be significantly small. So what I will do is, what we can say is that x, which is actually this, is the floor of this quantity. So 2 to the power 2n cube divided by 1 minus 2 to the power minus 2n square into x. Okay. And I can write this as, so I just multiply both numerator and denominator with 2 to the power 2n square. This is not 2n cube, this is 2 to the power 2n cube. So multiply both numerator and denominator with 2n square, so I will get 2 to the power 2n cube plus 2n square divided by 2 to the power 2n square minus x. Okay. So again, so what I am trying to say here is that, observe that this quantity that I am computing here is kind of greater than the actual value of x, right, greater because I am taking some additional terms over here. Okay. But the point is that those additional terms are not contributing much, because if I just take the, because x ultimately is an integer. Okay. So if I just take those additional terms, but I take the floor, that will actually give me the value of x, because those additional terms are only going to be you can actually estimate that. Okay, you can show that those additional terms, that is if you take the terms from I equal to n up to n going to infinity, that total summation will be less than 1. You can actually again prove that, because that quantity is less than 1, I can take the floor over here and this will be actually my x that I want. So what do I have here? So given x, I just have to compute one division, take the floor of it, and that's it. I get the value of all the powers. Okay. So doing one division gives us x. Okay. So now let us move to a actual problem related to this that we can.
How do I get the power?
Now you can just read it out. Na? So you have once you have x, you can read it out in blocks. So whichever one you want, whichever power you want, you can read out that specific block. You know that they are exactly spaced, how they are spaced out. So to get the ith power, you know you have to look at this particular position in the string.